Moving next to the small scale problems. These are problems that happen once you get to the distance scales of individual galaxies and smaller. The reason why these problems I'm about to talk about aren't immediately like, oh wow, this is it. We've ruled out dark matter. This is a massive problem. Is that these small distance scales are precisely the distance scale where it's very difficult to predict what will happen because of all of these effects due to stars and supernovas and neutron star collisions, which are extremely explosive and push matter all over the place. And even though they're only going to push the ordinary matter and not the dark matter, if you have a star that explodes and emits a bunch of matter, ordinary matter, that ordinary matter is now here. And the dark matter that was here is now being pulled by the ordinary matter that's moved out. So it will have an indirect effect on the dark matter. So predicting exactly what the universe looks like on these smaller scales is difficult. Of course, that doesn't mean that one can just throw one's hands up in the air and say, hey, these problems aren't real problems because it's difficult. I don't know what I'm doing. In the early universe where it's not so difficult, I can use dark matter and it's fine. These are still problems that should be thought about and addressed. So the first problem is called the missing satellites problem. And this is essentially that in the cold dark matter paradigm, as you go to smaller and smaller and smaller distance scales or mass scales, there should be structures at basically all masses. So we know there's a structure at the Milky Way's mass because we have the Milky Way, we have Andromeda, which is nearby. We know that there is some structure at like the Magellanic Cloud mass scale because there's the large Magellanic Cloud, the small Magellanic Cloud, which I think are about a factor of 10 smaller in mass than the Milky Way. But the dark matter paradigm would say that there should also be structures at a slightly smaller mass and a slightly smaller mass and a slightly smaller mass, and that there's no preferred distance scale or anything or mass scale. But when we observe the Milky Way, once we get below this kind of Magellanic Cloud distance scale, we start to see fewer and fewer dwarf galaxies that should exist if cold dark matter is the full paradigm, but don't, or do exist but not in anything like the abundance that cold dark matter would predict. So that's one problem. The next problem is that simulations of the centers of collapsed objects of cold dark matter have what's called a cusp. So if I look at the density here or here or here or here as a function of radius, it starts off at, say, this value. As I go into a smaller distance, it has a cusp. It just spikes up like that, the density. But when we make observations, we see that the density increases, 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 and then kind of flattens out as a core, that the centers of these objects don't have these very, very sharp densities. They have a core. So that's another problem. The simulations of cold dark matter suggest cusps, observed cores. So those are the problems. As I said earlier, they're not like immediate, oh my God, we've ruled out dark matter problems, because it's hard to predict what's happening on these scales, because just running a simulation with only dark matter isn't enough, right? Because we do know that there are stars, supernovae, neutron stars, black holes, all of these things that are forming very explosively. And so the missing satellite problem might be solved just within the normal lambda CDM model, simply because there are dark matter blobs that are of this mass, perhaps, but maybe a supernova went off in one of them and spat out all the observable light, or maybe enough supernovae went on that this explosive pressure pushed all of the ordinary matter out, and now there's simply just no stars inside these dark matter blobs. Maybe they exist, but we can't see them. And we would hope to eventually see their gravitational effect due to things like lensing, but we just haven't been able to see it yet. The cusp problem versus the core observation is a very, very similar problem, potential solution, that there might be in these larger density cores enough supernovae and things going off that eject enough enough ordinary matter, that then this ordinary matter that's out here actually pulls on the dark matter, and you get a flattening out of what would have been a cusp into a core. And then that's why we observe that. These are ongoing research of whether that is enough. It's easy to say that these effects could explain it, but to show conclusively that they do is a different matter. What are the more exciting possible explanations of this beyond just, it's just messy astrophysics? So warm dark matter is one. Warm dark matter would act exactly like neutrino masses, by the way. So neutrino masses are a form of warm dark matter. Warm dark matter, as opposed to cold dark matter, is just meaning it has some temperature, it has some non-zero velocity. It's traveling through the universe with some speed. Therefore, it doesn't fall into the small wells. It only falls into the big ones. Neutrino masses themselves, there's just not enough mass in neutrinos, not enough proportion of dark matter for it to solve these problems. But if there's some other component of dark matter that is also warm, like neutrinos, then exactly as I was saying earlier about how neutrinos don't fall into the small wells, the warm dark matter also wouldn't. And if you've got enough of the dark matter being warm dark matter, you start to see why a missing satellite problem is not so much of a problem, because you're just not predicting that they exist anymore, because there's so much warm dark matter that these smaller distance scale and therefore smaller mass satellites just don't form. And the cusps as well, you don't get this big spike at the center because so much warm dark matter is unable to fall into the center because it has too much thermal energy. It's traveling too fast. So if there was a subset of the dark matter that was warm dark matter, it would solve this problem. There's another very similar solution called fuzzy dark matter or ultralight dark matter or wave dark matter. It's dark matter that is so light and like much lighter than the neutrinos, lighter than anything we've ever encountered. Measured in electron volts, this would have to be, so remember I was saying that some of the neutrinos must be 0.06 electron volts. This light dark matter would have to be as light as 10 to the power of minus 21 electron volts before it becomes interesting for the effect I'm about to talk about. But those who have a very basic quantum mechanics might have heard of the de Broglie wavelength, which is this idea that matter has a wave-like quantity. Now, the de Broglie wavelength is something like an electron. It's very, 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 very small, of the order of, I guess, the size of a sort of internal size of an atom, not the nucleus, but the atom itself, the sort of outskirts of the atom. But the de Broglie wavelength depends on the inverse of the mass. So a smaller mass means a bigger wavelength. Now, if you have a mass that is 10 to the minus 21 electron volts, you have a mass that has a de Broglie wavelength of the order of the sizes of these missing satellites, of the centers of these cusps of the more massive, like the Milky Way halos, density profiles. So if some proportion of the dark matter was fuzzy dark matter or wave-like dark matter or ultralight dark matter, just different names for exactly the same thing if you happen to be Googling and see these terms, then you would also solve these problems of missing satellites. Missing satellites just because the wavelength of these things is so large that they can't cluster any more on any smaller distance scales than that. They just, a wave wants to disperse, and on any smaller distance scale than the wavelength, it will disperse. The other possible explanation is modifying gravity, saying that gravity inside galactic scales isn't general relativity. It's some modification of general relativity. We've measured the effects of general relativity extremely well on solar system scales. All of the planets seem to be doing exactly what they're meant to be doing. We've measured it relatively well on the horizon of the observable universe scales and the CMB and things. But there is this intermediate scale, like a galactic scale, where in some sense we've measured it quite well. And if you don't have dark matter, we've measured it to be wrong. If you put dark matter in, then everything fits, except for these small scale problems. So the argument would be that there is some modification of general relativity on those particular distance scales. So originally, I think the hope had been that one could do away with dark matter entirely, but then the CMB got measured more accurately. So I'm talking about originally meaning like the 80s or 90s. And now that the CMB has been measured so accurately that it, for reasons I explained earlier, just absolutely requires dark matter. Now you either have to just modify gravity, but keep dark matter so that the modification of gravity alters this local environment a little bit, but isn't entirely responsible for all the effects of dark matter. Or if you really do want this modification of gravity locally to explain all of the effects of dark matter, you have to explain what happened to the dark matter. Where did it go? So those are the problems that those models face.